What are the best space propulsion technologies to produce clean energy? Space propulsion technologies, traditionally developed for space exploration, are increasingly being studied for their potential to support clean energy production on Earth. While these propulsion technologies are not directly used to generate clean energy, their innovations could drive advancements in energy production systems by contributing to more efficient energy transfer, resource extraction, and space-based energy harvesting. Below are some key space propulsion technologies with potential clean energy applications. 1. Electric propulsion, ion and Hall thrusters. How it works. Electric propulsion systems use electricity to ionize gases, e.g., xenon, creating ions that are expelled to produce thrust. These systems are highly efficient and require far less fuel than chemical rockets. Clean energy potential. Energy transfer and satellites. Efficient satellite deployment and station keeping reduce the amount of space debris and fuel waste, making space missions more sustainable. Space-based solar power, SBSP electric propulsion can enable satellites to maintain precise positions for solar power harvesting systems in space, enhancing their long-term viability. Lower emissions in space travel. Ion and Hall thrusters produce very little pollution compared to chemical propulsion, potentially reducing the overall environmental impact of space exploration and related activities. 2. Solar electric propulsion, SEP. How it works. SEP systems use solar panels to generate electricity, which then powers ion thrusters. These systems are extremely efficient and capable of long-duration missions, requiring less fuel and producing low emissions. Clean energy potential. Sustainability in space exploration. SEP reduces the need for chemical propellants, leading to cleaner, longer-lasting missions. Space-based solar power. By using solar energy to power propulsion systems, SEP supports the infrastructure for harvesting solar energy in space, enabling continuous power generation with minimal environmental footprint. 3. Solar sail propulsion. How it works. Solar sails use the pressure of sunlight to propel spacecraft. The sails capture photons, creating a continuous, albeit low, thrust without consuming fuel. Clean energy potential. Fuel-free space missions. Solar sail technology eliminates the need for traditional fuel, providing a completely clean propulsion method. Energy infrastructure support. Solar sails could be used for positioning solar power satellites, reducing the need for fuel-based repositioning systems and supporting space-based solar energy collection. Asteroid mining for clean energy materials. Solar sails could enable long-duration missions to mine asteroids for rare metals and minerals used in clean energy technologies like solar panels and batteries, supporting sustainable energy infrastructure on Earth. 4. Nuclear electric propulsion, NEP. How it works. NEP uses nuclear reactors to generate electricity, which then powers ion or plasma thrusters. These systems could provide efficient, high-power propulsion for deep space missions. Clean energy potential. Space-based energy systems. NEP could support long-duration, high-power missions that are critical for space-based energy harvesting technologies, such as large-scale solar power arrays in space. Efficient resource extraction. NEP could enable missions to asteroids and other celestial bodies to extract resources necessary for clean energy technologies, reducing the environmental impact of Earth-based mining. Safe nuclear innovations. Research into NEP could drive advancements in compact and safer nuclear power reactors, potentially benefiting Earth-based clean energy production. 5. Fusion propulsion. How it works. Fusion propulsion systems, still in development, aim to harness nuclear fusion reactions, similar to those that power the Sun, to generate massive amounts of energy and thrust. Fusion propulsion would use light elements like hydrogen as fuel, fusing them into helium and releasing vast amounts of energy. Clean energy potential. Fusion energy breakthroughs. Advancements in fusion propulsion could drive breakthroughs in nuclear fusion as a terrestrial clean energy source. Fusion reactors on Earth could produce vast amounts of energy with minimal environmental impact and almost no radioactive waste. Long-term space missions. Fusion propulsion could enable long-duration missions to support space-based solar power infrastructure and asteroid mining, crucial for future clean energy systems. Fuel efficiency. Fusion propulsion requires far less fuel and produces much less waste than conventional propulsion methods, aligning with the goals of sustainable and clean energy systems. 6. Magnetic plasma propulsion, VASIMR. How it works. The Variable Specific Impulse Magnetoplasma Rocket, VASIMR, uses radio waves to ionize a gas, turning it into plasma. Magnetic fields then accelerate the plasma to produce thrust. VASIMR offers variable thrust and fuel efficiency, making it ideal for long-term missions. Clean energy potential. Sustainable space missions. VASIMR's efficiency reduces the need for large amounts of fuel, minimizing the environmental footprint of space missions. Asteroid mining for rare metals. This propulsion system could support resource extraction missions to provide materials for clean energy technologies like solar cells and energy storage solutions. Space-based solar power. VASIMR could power satellites and space stations that maintain solar power infrastructure in orbit, contributing to sustainable space-based energy generation. 7. Beamed propulsion, laser and microwave propulsion. How it works. Beamed propulsion uses ground-based or space-based lasers or microwaves to transfer energy to a spacecraft, which absorbs the beam and converts it into thrust. This allows the spacecraft to be powered remotely, without carrying heavy fuel supplies. Clean energy potential. Space-based solar power. Beamed propulsion is highly relevant for space-based solar power systems. The same technology that beams energy to propel spacecraft can also be used to beam solar energy from space to Earth. No onboard fuel requirement. By eliminating the need for onboard fuel, beamed propulsion reduces the overall mass and environmental impact of space missions, supporting sustainable space operations. 8. Chemical propulsion for clean fuel research. How it works. Traditional chemical propulsion systems use chemical reactions to produce thrust. While these systems are less efficient than electric propulsion, they remain useful for short, high-thrust missions. Clean energy potential. Green propellants. Ongoing research into eco-friendly propellants for chemical rockets, such as hydrogen peroxide or bio-based fuels, could lead to cleaner rocket launches with fewer emissions, contributing to sustainable space travel. Hydrogen research. Technologies developed for chemical propulsion using hydrogen as fuel could lead to innovations in hydrogen fuel cells and storage, supporting the growth of hydrogen as a clean energy source on Earth. Space propulsion technologies, while primarily used for space exploration, are driving innovations that can influence clean energy production systems on Earth. From efficient resource extraction to space-based solar power, these propulsion systems offer pathways to a sustainable energy future. What are the space-based technologies to produce vegan products, plant-based energy systems and artificial photosynthesis systems? Space-based technologies are not only advancing space exploration but also have the potential to transform food production, plant-based energy systems, and artificial photosynthesis. Below are several space technologies that could help produce vegan products, support plant-based energy systems, and enable artificial photosynthesis. 1. Space-based agriculture and vegan food production. Space exploration has driven significant advancements in controlled environment agriculture, which can be applied to produce vegan products both in space and on Earth. These technologies help create sustainable, plant-based food systems. Hydroponics and aeroponics. NASA has developed hydroponic and aeroponic systems that grow plants without soil, using water or mist with nutrient solutions. These techniques allow plants to grow in space or in controlled environments, reducing water and space requirements, which is ideal for producing vegan food products such as vegetables, legumes, and fruits. On Earth, these technologies can be used in urban farms and vertical agriculture, where space and resources are limited, enabling a more sustainable, plant-based food production system. Bioreactors for plant-based meat. Space-based research has led to the development of bioreactors, which can be used to grow plant-based proteins and even lab-grown meats. Companies like Aleph Farms and Impossible Foods are already experimenting with bioreactors in space to grow cell-based meat and plant-based proteins without animal farming. These bioreactors could revolutionize vegan food production by creating high-protein, plant-based alternatives to meat, reducing the environmental impact of traditional agriculture. Space-driven genetic engineering for plants. Space agencies like NASA are exploring how genetic engineering and CRISPR technology can be used to modify plants for better growth in harsh environments like space. On Earth, this research can be applied to develop climate-resilient crops that can thrive with minimal resources, supporting more sustainable vegan food production systems. Space-grown crops may offer new plant-based products with enhanced nutritional profiles or unique properties for vegan food markets. Algae cultivation in space. Algae is being studied for its potential as a high-protein food source for astronauts. It grows efficiently in controlled environments, requires minimal resources, and can be used to produce various vegan products, including supplements, protein powders, and plant-based oils. Microalgae farming in space provides insights for scaling up algae-based food systems on Earth, offering a sustainable protein source for vegan diets and even plant-based biofuels. 2. Space-based plant energy systems. Space technologies contribute to developing plant-based energy systems, which can reduce reliance on fossil fuels and contribute to cleaner energy solutions. Space-supported bioenergy research. Biomass energy systems convert organic material, such as plants or waste products, into biofuels or electricity. Space-based experiments, such as those conducted on the International Space Station, ISS, study how plants grow in microgravity and other extreme conditions, providing insights into how biomass can be grown efficiently with fewer resources. Space technologies can support the optimization of bioenergy crops, ensuring they grow faster and yield more biomass, which can be converted into clean energy for both space missions and Earth applications. Photosynthesis optimization through space research. Artificial photosynthesis systems are being developed to replicate how plants convert sunlight into energy. Space research focuses on how light, CO2, and other factors affect photosynthesis in controlled environments. These findings can be applied to design high-efficiency photosynthesis systems on Earth, which would enhance the growth of bioenergy crops. Artificial photosynthesis systems could provide sustainable energy by mimicking plant processes to produce clean fuels such as hydrogen or methanol from sunlight, water, and CO2. 3. Space-based artificial photosynthesis systems. Artificial photosynthesis is one of the most promising technologies for producing clean fuels from sunlight. Space-based technologies contribute to its development in several ways. Solar energy harvesting systems. Space-based solar power technologies, developed for energy harvesting in space, can provide insights into improving solar energy efficiency on Earth. Space-based solar panels operate continuously without weather or day-night cycles, leading to significant innovations in solar energy conversion. Space-based research in solar cells and energy storage could accelerate the development of artificial photosynthesis systems by improving the efficiency of light harvesting materials. Catalysts for artificial photosynthesis. Artificial photosynthesis relies on catalysts to convert sunlight into chemical energy, mimicking the natural process of plants. Research in microgravity conditions helps scientists understand how catalysts behave under different physical constraints, leading to the development of more efficient catalysts for artificial photosynthesis. These space-based experiments could result in breakthroughs for Earth-based systems, enabling large-scale production of solar fuels and hydrogen using artificial photosynthesis, effectively creating clean energy from plant-like processes. CO2 capture and conversion in space. Space technologies designed for life support systems, such as CO2 scrubbers, are used to capture and recycle CO2 onboard spacecraft. These systems could be adapted for artificial photosynthesis technologies on Earth, where CO2 capture and conversion are crucial for turning waste gases into usable fuels. By combining CO2 capture systems with artificial photosynthesis, clean energy can be produced while reducing atmospheric carbon, contributing to climate mitigation efforts. 4. Space-supported vertical farming for vegan products. Vertical farming, supported by space technologies, is becoming a critical component of sustainable food production, especially for plant-based and vegan products. Controlled Environment Agriculture, CEA. Controlled environment agriculture systems developed for space missions allow for precise control over lighting, temperature, humidity, and nutrients, ensuring optimal growth conditions for plants. On Earth, these systems are applied in vertical farms to produce vegan food with higher yields, less water, and no pesticides. This approach enables year-round production of crops like leafy greens, herbs, and fruits, essential for vegan diets. LED lighting systems. LED lighting developed for space missions can provide plants with the optimal spectrum of light for photosynthesis, enhancing growth rates and improving energy efficiency in plant-based production systems. These advanced lighting technologies are key components of vertical farming and can reduce energy consumption while maximizing plant growth, supporting sustainable production of vegan food and bioenergy crops. 5. Space-based fermentation for vegan products. Space-based research has also influenced the development of fermentation technologies, which are critical for producing plant-based proteins and vegan products. Microbial fermentation. Microbial fermentation technologies, studied in space, can produce proteins, enzymes, and bio-based materials with minimal resources. These systems are used to create plant-based meat alternatives, dairy-free products, and vegan proteins. Space-based fermentation research contributes to creating scalable, eco-friendly processes for producing vegan foods and plant-based materials on Earth, reducing the need for animal farming and lowering the carbon footprint of food production. Space-based technologies are driving innovations that support the production of vegan products, plant-based energy systems, and artificial photosynthesis. From controlled environment agriculture and bioreactors to space-supported solar energy harvesting and artificial photosynthesis systems, these advancements are helping to create sustainable, plant-based solutions that can contribute to both food security and clean energy production on Earth. By leveraging the knowledge gained from space research, we can develop technologies that lead to more efficient and environmentally friendly systems for food and energy production.